All right. Woo.
Thank you.
All right. Annie's with us too from NRCS. She's
Yeah.
gonna be
Literally and figuratively.
learning the ropes, as we say, as I transition out to retirement.
Oh, yeah, we've heard this one. You're retired as much as Peter and I are.
Right. I got to pop up here. That's good. All right, welcome. I'm going to share my screen. Let me know if I'm hearing well and everything like that. I'm probably not seeing any chat, so if any or someone sees it, just hop in and feel free to ask a question anytime. I always like to.
You're on, Jim.
Okay, you can see my screen.
Yes.
All right, I always like to start showing dirty pictures of soil. You still on here?
Yes.
Okay, all right. It's this 2-monitor thing there. So just going to show examples of what a soil scientist sees when I dig a hole and look down that hole and observe the soil. I look at it, I classify it, determine properties, about 80 different interpretations worth, and then I map it. So this is just an example of a soil profile showing what we call the master horizons or layers. We'll be going into these, what they mean, O, A, B, and C. I always like to say soils is pretty easy. If you know your A, B, and C, you can know your soils there. So just showing some different examples. This soil is called the Deerfield Loamy Sand. It's a moderately well-drained soil that's formed in glacial outwash material, which we'll be learning about. I got a phone ringing now.
Jim, do you want to go into presentation mode so that way it's
I'm not into presentation mode?
Not yet.
Ah, shit. Sorry.
Oh, look, just take slideshow over.
Oh, so you're not seeing the profiles?
Well, we see it.
We're seeing the profile, just not the slideshow.
Oh,
We're seeing the slideshow, but we're seeing all this other stuff.
okay. It's probably because I got 2 monitors. Maybe I should.
No, Jim, I think you just needed to hit the slideshow button down at the bottom right-hand corner of the PowerPoint where
And
it
then
has
stop beginning.
Okay. Can you see it now, big screen, or no?
No.
No, you stop sharing your screen.
See, I don't like the Zoom stuff. All right, hold on. I got to figure out which screen to show. PowerPoint. No, it's not showing up on my monitor. Dang it. Shoot.
There we go.
There you go.
All
right.
Beautiful.
All right, so now you're seeing that top screen.
Yep.
All right. Better?
Deerfield Loamy soil.
Okay. So you can see a Deerfield soil, right?
Yes.
Okay. All right. Sorry about that. Technical difficulties. So yeah, Deerfield soil, it says it's moderately well drained. That tells me that it's got a drainage issue. It's not very wet, but it's wet enough to have wetness issues that I can see in this lower horizon with those blotchy colors in that C horizon. Above that, the topsoil is a really thick, dark colored material, and it has a very abrupt boundary. That's telling me that that soil has been plowed and farmed for agriculture. Below that, I have a BW horizon, which is on a bright colored horizon. Basically, iron oxide is coating the sand, silt, and clay and giving it a nice yellowish brown color. That means that horizon's well aerated and doesn't have any issues with wetness. The horizon below is gray with blotchy colors. We call those redoxymorphic features. So we'll be learning about those. Let's show a few more. Go next. All right. Hopefully you can see the Woodbridge. Completely very similar as far as drainage, moderately well drained. This soil, though, formed in a dense glacial till deposit. So it still has a plow layer. It has that bright BW. When you dig down into that 2CD layer, it's a very dense material, very high bulk density, difficult to dig through. The backhoe actually had trouble digging through this soil, kind of stood right up on its back to get through it. And that's a restrictive layer that's perching the water. So the other soil had what we call an apparent water table. This soil has a perched high water table, but still causes major issues with wetness and trying to get a septic system located on it.
Jim, what does perched mean?
Perch means it's not the actual aquifer. It's just being held up by that restrictive layer, usually during the wet season, which starts about now, December, all the way up until the vegetation comes out and starts to pull that water out by evapotranspiration. So it's just perched
Yeah.
up for a certain amount of time.
We have a question. Were plows all the same depth, or can the AP be used to date field use?
No, the plow is, obviously, when we first broke the ground, the plows were not probably very, have the horsepower that they do today. So originally they were probably just a lot shallower. Nowadays they can plow anywhere from, if I see an A horizon that's more than say 3 or 4 inches thick, to me, it's been plowed. Actually the profile you're looking at here, right at that 5-inch zone, that's what an A horizon normally looks like if it's never been plowed. So that's a very thin layer. So we do have some very deeply plowed soils. They have a chisel plow in some situations where they need to break up a restrictive layer such as a plow pan. But typically the plow layer is, anywhere between 3 to 12 inches thick or so. And it really depends on how long it's been an ag and how much horsepower that farmer had. So this soil is called the Carver Core sand. It's basically associated with pitch pine and scrub oak. You would find this all the way out on Cape Cod, southeastern Massachusetts, Plymouth County, where I did a lot of mapping with. And it just shows a nice, well-drained forested soil with an organic layer about 4 inches thick, very thin A horizon, and then right into that B horizon. And this B goes all the way down quite deep, and it's basically just coarse sand from top to bottom. So it's a very dry, sandy type of soil. This is called a Pequodnik soil. This is actually right up the road from my house. And it shows that till is a very black colored in nature. And that's because it's derived from the Narragansett Basin, which is a completely different rock than we have in our granitic upland areas of Rhode Island, the Northwest Hills, as I call them. So if you ever come over the Newport or the Jamestown Bridge, you'll start seeing all the rocks are black in color and stratified. When the glacier went through there, it broke up that shaly Carboniferous age rock and deposited it as till. The stuff above it is
Tim?
actually windblown sand. Yep, go ahead.
Sorry. Where do you usually see plowed soils?
Everywhere. Yep. If you study the land use of Southern New England in particular, 70, Paul could probably know better, 70% was cleared of trees, farmed. That stayed until until settlers started to find way better soil out west that didn't have a lot of rocks. They didn't have to build the stone walls to clear the fields, and the soils were actually much better. So it's very rare to actually dig a soil in Rhode Island and not have a plow layer. I actually went out to some places I would never expect to see a plow layer, a little tiny island, or, in the middle of Ninigret Pond. I dug it and it had a thick plow layer. So at some time somebody cleared the trees on that tiny island to grow crops. So very rare to not find a plow layer. Little hint there, if you have a soil test pit, we could have some. And actually, if you watch the video, there's one where the soil pit is in a mature hardwood forest with huge trees, and there's a nice thick plow layer on it. So that's on the video if you watch it, which Pete will send the link to those videos there. Just again, another moderately well-drained soil. I'm not going to spend too much time, but we do collect a lot of data on soil. That's how we build our interpretations. We sink monitoring wells to monitor the water. We actually record the temperature of the soil. We do a lot of laboratory analysis, spend a lot of time collecting data in soil survey. We're not making all this stuff up when we pull these interpretations there. This just shows you a nice outcrop of a glacial till soil. We'll talk about the parent material and our two major types of glacial deposits that we have in New England here. Glacial till is just unsorted, unstratified, heterogeneous mixture of all your particle sizes. So you get anywhere from clay all the way to that large granitic boulder that was plucked way north up in Fall River and deposited down here in Little Compton by the glacier. Just a few more. Northwest Hills, I mentioned, we have a lot of bedrock or shallow to bedrock soils. If you ever drive a highway and you see where they had to blast through to put the road in, that's because they hit the Earth's bedrock or the hard ledge. So we have a soils here that have different depths to bedrock. So we would have different soil series associated with those soils based on the depth to hard rock. And you can imagine the interpretive issues trying to put a house with a foundation or a road or something on here. Wetland soils. This is a classic example of what we call a very poorly drained soil. We have a very thick organic layer. That black material is not mineral soil. It's actually organic. It's an O horizon. And anytime you get thick organic horizons underlain by really gray soils, that's what we call a hydric soil. And these are subject to wetland protection associated with wetlands, but also have a lot of value as far as being a carbon source or a carbon sink and sequestering carbon and filtering out any nutrients that we may put into the water. We do one more, and that's just showing that soils can also be used for cultural resources. The mound you see in the upper right is actually was a buried Native American corn mound that was discovered when a person wanted to put a dock in Cape Cod. He had to apply for a federal permit, and an archaeologist went out there and saw this mound buried under about 2 meters of windblown dune sand. And it turned out to be a major settlement site there. They actually took the image on the bottom is a radar profile that I was asked to map out the boundary of this corn mounds here. And they actually took the data that I did and made that little postcard on the left-hand side. So that was pretty cool. Any questions so far? I'm going to switch over to the regular PowerPoint on soils. So I'll cover some of this stuff in more detail. All right, it says screen sharing has stopped. Now I got to reshare, right? Let me see if I do this one right. All right, can you see that one now?
Yeah.
All right, I forgot to open with Happy World Soil Day. So today, December
Yes, it is.
December 5th is World Soil Day. Can you still see it? Good, okay. So World Soil Day is just something we celebrate every, it's an international day of celebrating soil. We always try to get it trending on some of the social sites. We haven't yet, but maybe someday we'll get it there. So I actually picked a good day. I didn't even know when I picked it that it was World Soil Day until I checked my calendar. So,
Jim, show the slideshow.
oh,
We're seeing it's your one screen.
all right.
He's just so excited over Will Soil.
Yeah, I know. All right, I gotta figure out which screen I need to show. So on mine, it's showing the right one. Let me do a stop share. So I think I gotta share the other one. So that would be not this one here. And then let me pull up that. Oh, let me pull up that one. How about now? Is that working?
No, that's the old one.
Past.
Even now? That's weird because it's on my monitor here. So you're still seeing the old slideshow.
Yes.
All right. Dang.
Stop your share.
Yeah.
Go back.
You think we've been doing this long enough that I could figure it out, but I'm having issues with my I think it's because I have two monitors. All right, let me do this again. Share screen. I want to share not whiteboard. I want to share this one here. All right. So you can see that, but it's not in
Yes.
PowerPoint mode, right?
Yeah, now go up to where it says slideshow.
Yeah.
All the way at the top.
All right.
Keep going over.
Left.
Left.
Yeah, it's not moving.
New share. No.
No. Not
Sure.
all the way to the top. Just on that window.
Yeah.
See where it says
Oh, yeah,
slideshow?
Yeah, I can. All right. Slideshow. Hang on. Slideshow. Got it. Not now.
I'll go to the front beginning.
Now?
Yes.
Yay.
We do have a question, and it was, what is the shallowest water table that you can build houses on?
Ooh, that's a tough one. In Rhode Island?
Yeah.
All right, I won't go there. So the regulations are for a septic system. So if it's a house with a septic system, If it's less than 18 inches, you would need a variance to put a septic system in, and they would probably require you to do a pretty expensive, what's called a denitrification or a bottomless sand filter type of system. If anybody has a little sandbox looking thing in their backyard, that's a what's called an alternative septic system designed to treat the nitrates better before it gets into the groundwater. The other thing that would limit developing a house would be whether or not it is a wetland or in a wetland. So if it has a water table within, I would say probably, what's the hydrology? I should know this right off the top. Probably also like 24 inches. If you have a water table within 24 inches, it probably is going to be a hydric soil. So I would say within 2 feet. You can. And then with the wetland, if you are in a wetland, you still need to meet a setback requirement. So 50 foot from the wetland, which is where you would put your house. So good question. But wetlands are also determined not just by soils, but also hydrology and vegetation there. All right. So for the Envirothon, again, I'm Jim Tureen, Assistant State Soil Scientist. We will put the I'll load this presentation to that site as soon as I'm done. I'll give it to Paul or Peter to load up there. So this is one of our sites that we use where we actually had a nice backhoe pit. I want you to probably pay attention to the special topic, which I guess this year is in New York, Geneva, New York.
Yeah.
Never been there. I don't know anything about the soils, but I would definitely look around, especially if you're the winning team going. I recommend you doing your research on what the soils are out there and do that. They did say the study guide for the soils would be posted in May 2024. So set your calendars, and once that's posted, take a look at it. And if you have any questions, you can email me. So the topic is renewable energy for a sustainable future. Think about how soils would relate to this topic here. And I got some ideas at the end. I did check our web soil survey where we get our soils data now, and we do have some interpretations for renewable energy, solar array, anchor-based systems, whether or not the soil can support solar arrays and stuff like that. So we're always adding new data to our soils that I didn't even know this existed here. So for the competition day, basically sometime in May, I believe, it's going to be a combination of multiple choice, fill in questions about soils. Encourage you to review all the online material, this PowerPoint, to help you with that. There will be a soil pit, hopefully hand dug. Last year we couldn't dig a pit due to some issues there, where you're going to hop into the pit and describe the horizons, color, texture, determine the parent material, and some interpretations about what you see in the soil. There's also a section on using a printed soil survey data from the web soil survey using a customized soil report. We don't actually allow use of computers or smartphones, so you're going to have a printed version of this of the soil survey. So try to study everything. Soil science. Oh, yep. Question.
Will this video be posted at? Okay, I guess Peter answered the question. The recording will be posted. Sorry.
Oh, okay. Yep. In case you missed it.
And this year, when talking to the people at Camp Hoffman, he can lend you, he has a backhoe.
Oh, you told where it was.
Well, they've known this for a month or so.
Okay, Camp Hoffman. That's down.
Ministerial Road. Yeah.
Oh, all right. Oh, I know.
He will give you, you'll get his information and work out something with him. So, I mean, obviously, once again, it's a camp, so there's a lot of areas that have been disturbed.
Yep.
So you'll have to find an area, you know, that hasn't been.
Okay, so I'll have a backhoe pit. That's good. Answers that question. Right. Any other questions or? Yeah, there's also videos that I posted during COVID. I went out and actually just shot some videos that you might want to take a look at too, out at East Farm. So soil science is pedology. I'm a pedologist. It's a scientific study including soils, where they come from, how they're made, some of their characteristics, and mainly about the uses. So one of the major things we do in soil survey is we provide interpretations of what the soil's limitations are, what it's used for. Is it good for agriculture, trees, roads, buildings, and that sort of thing? So again, we have over 80 of these soil interpretations that are built into our web soil survey, and continually adding more as we increase our soils knowledge. This profile is from a Narragansett silt loam, which is the unofficial state soil for Rhode Island. The name Narragansett, that's the soil series. That's typically named for where that soil was first classified and mapped. So if you're wondering where we get these names from, it's basically named after a village or a geographic area where that soil was kind of first classified or discovered. Why do we study soils? Whole reasons. I always ask people, if you try to think of something that doesn't involve soils, it's pretty hard. Crops, agricultural uses. We home to many organisms. I have a nice little colony of bees in my backyard that live in the soil that come out first. They're the first insect to come out. Usually the first day of spring, they'll come out in my backyard, and they're living in the soil right now. It's an essential natural resource. Also gives you a snapshot of geologic time and climate, biological and human history. A good soil scientist can read the layers and interpret what happened in that soil over the past X amount of years since it's been developing. Another major use is as a carbon sink. I think I have a slide up here that Earth soils contain 250,000, 2,500 gigatons of carbon, more than 3 times the amount of carbon in the atmosphere and 4 times the amount stored in living plants and animals. So it's a major carbon sink for keeping the carbon from going into carbon dioxide and causing things to warm up, as they have been pretty rapidly. Definition of soil: it's a natural body, occurs on the land or water. We actually map soils underwater, particularly here in Rhode Island. Occupies space, and it's characterized by one or both of the following. We like to see these horizons or horizontal layers in the soil that are formed under soil forming or pedogenic processes, and also the ability to support rooted plants in a natural environment. And I always say that dirt is soil removed from its natural environment. So dirt is the stuff that's in your clothes that you wash out or on your hands and stuff like that. So there's a difference between dirt and soil. Where do soils come from? The gentleman on the left there, or maybe you're right, is Hans Jenny, 1939. He wrote The 5 Factors of Soil Formation, and it kind of is the book that set soils as on a different course from geology or geologic material. He related the soil that we see in this picture here as a result of the biota or biology, the organisms, macro and microorganisms that are living in the soil, doing stuff to the soil, adding carbon as the leaves fall off a tree, microbes that are digging in the soil, worms, that sort of thing. The climate, whether a soil is dry or wet, we have major differences in the soil, hot or cold. Just think about the differences between a soil up in Alaska versus down in the tropics, such as where this was from. You're going to get major differences in the soil. Parent material is the geologic material the soil formed in. This would be a volcanic soil here. So those rocks are volcanic, and the soil above it just weathered right in place. There was no glacier in this area to deposit that material. The topography is another major thing, is how steep the soil is. You can see this soil is very steep. That's probably a 45% slope. And as a result, the soil is very shallow to the hard rock, which is where that arrow is for the parent material. That's the hard rock right there that you see. If a soil is on a level slope, it's going to get a lot. Material is going to be eroding off the hills and deposited into the flat areas. Convex slopes tend to shed water. Concave slopes tend to attract water. So topography is a very important soil forming factor. And all of these 4 over time, whether a soil is young or old, most of our soils in New England are very young. They've only been forming for about 10,000 years. So we have very young soils in our area. And that's your soil horizon right there. That's actually a mollisol down in Tortola.
Jim,
Yes.
we did have a question, but I'm a little just unclear on the question from Situate Middle School that said, what are some of the differences? Does Situate Middle School have like a mic that maybe they can talk into?
Differences in parent material or just
I
differences?
was trying to ask them that. They haven't answered yet.
I'll keep going and
Okay.
drop in on me. If they
What
do.
are some of the differences of tropic soil and cold area soils?
So tropical soils, actually, if you're like in a rainforest and you get more than 200 inches a year, the soils are actually, there is an entire soil order called oxasols, and they're characterized as basically having no nutrients at all in them. All the nutrients and everything has been leached out from the heavy precipitation, moved down or moved out of the soil. So one of the reasons the importance of rainforests to keep them forested is if you cut those trees, you're basically developing a soil that has no natural fertility in it, and they're very hard to grow stuff on it. It's that living tree that drops the leaves that provides the nutrients for that soil. So, you know, the issue with rainforests is they can grow corn on them for a few years, but then they have to really add a lot of fertilizer, and, you know, goes right into the Amazon River and that sort of thing. And the other one was the cold areas. You would have, basically we have permafrost in a lot of our soils. There's another soil order. We have 13 soil orders now, and those are called gelisoils. And those are soils that have a permafrost or a permanently frozen layer in the soil. And an issue with those is now that they're starting to melt, they're releasing a lot of methane that's stored in those soils. And methane is a major greenhouse gas. I think it's even worse than carbon dioxide. So major issues with those soils warming up there.
One more question.
Yep.
Are they going to have to determine slope with a clinometer as
Yep.
part of the soil section? For
Yep.
Okay.
Yep. There'll be one question where you have to measure the slope. So make sure you know how to use a clinometer. Forestry, I know you use one also. We do percent slope. So if you're not familiar with that, and I don't know if there's a field day set up or anything like that, make sure you know how to use a clinometer.
There'll be a field day at the end of April.
Good. We'll show you how to use one then. Right. So the foil factor parent materials, the geologic material the soil formed in, a lot of different types. What that determines in the soil are the types of minerals, you know, either from the rock or from the expulsion of this volcano you see. Reaction of the soil. When we talk about reaction, we mean whether it's acidic or basic, the pH of the soil. The color, I mentioned that dark carboniferous color of the till from the Pequodnik soil. That was because of the bedrock had dark color to begin with. And also a lot of the chemical physical properties. I think out in New York, they actually have calcium carbonate or limestone in some of the rocks. So you might have soils that have high pH in those soils. Most of our soils here derive from acid granitic type of rocks. So our soils tend to be quite acidic. Our pH range is about 4.5 to 5.5. Our New England parent materials, I kept talking about glacial. All of New England, all the way out to Block Island, was covered by ice about 26,000 years ago. It was called the Wisconsin glaciation. It was the last glacial advance, following about a series of 3 other ones before that. Each of those advances were followed by an interglacial stage. Whether or not we're in one now, and we're going to have another glacial advance is subject to time to tell. So right now we are in what's called a Quaternary period that began about 11,000 years ago until now, and geologists are debating whether we've entered a new period called the Anthropocene, where humans have changed things so much that we're a new epoch, basically. So I mentioned that during that Wisconsin in time, all of New England was covered. The actual terminal or final part of the ice sheet was formed Block Island. If you can see that map on the lower right, that shows you the retreat positions of the two lobes of ice that covered Rhode Island, the Point Judith lobe and the Charlestown moraine lobe. So Block Island was basically the terminal moraine, also Long Island, Martha's Vineyard, and Nantucket. And then by about 18,000 years ago, the ice was out of Rhode Island. So really quick coming down of ice, depositing material, retreating back up north. And once that ice was gone, we have what's called time zero in soil formation, and our soils begin to form. So the first or dominant parent material we have is called glacial till, unsorted, unstratified material. It was either deposited underneath the ice with a mile or so thickness of ice on top of it, or within the ice, such as the picture up on top is just a melt out glacial till. So they're the oldest of the superficial deposits overlying most of the bedrock areas. That map on the bottom shows you these oval shaped streamline hills. Those are called drumlins, and those are dense glacial till landforms that have that restrictive layer that I showed on some of the soil profiles. They also tend to be oriented all in the same direction, marking the direction of ice flow. So they're all pretty much from the north to south in that area. Some properties associated with till, there's two major types. There's something called a lodgement till that has that dense restrictive layer, and then a sandier, looser type of till. We called it ablation. Now it's referred to as superglacial meltout till. So anytime you start seeing large angular boulders, stone walls, start thinking that you're in a glacial till landform. And this is just some of the hydrology that we get with till, where you have that restrictive layer. You can be up on top of a hill and still have wetness. You can even have wetlands way up on top of the hill. We mentioned that perched water table. That is perched groundwater versus the actual true or apparent groundwater that you would have much deeper down on there. So those wells in the houses are actually going into the apparent or aquifer. But up above that, you can get this perched water table that will cause basements to flood, difficulty for crops to go in early in the season due to wetness. I'm in the wrong spot. The second dominant parent material we have is glacial fluvial, also called outwash. So the map on the bottom shows you at the time of its maximum extent of the ice, sea level was depressed by 300 feet. From modern day, so you could have actually walked out to almost past New Jersey during when the ice was at its maximum, and all of that water held within the ice was then released, and you had these monster meltwater streams coming off the ice, depositing stratified layers of sand and gravel within them. So the picture on top is actually the plumbing coming out of a glacier, and that little orange thing is a person on top. So it gives you an idea of the size we're looking at here. So during the summer, this thing is that entire tunnel has water just shooting out of it, depositing material there. So when we look at glacial outwash, we see that it's got stratified or layers of sand, gravel, mostly sand, maybe a little bit of silt, but pretty much predominantly sand. They tend to have very rapid water movement. So they're associated with aquifers, and they don't have those perched water tables. They're also kind of the soils that have very few limitations for most uses. So they tend to be the first developed in an area, but they're also tend to also be the best for agriculture. So there's always a battle for, glacial outwash land. Just some of the hydrology, you get very large pore spaces. So water moves very rapidly through these soils, almost too rapidly, whereas they don't treat the material going into the aquifer. So there could be issues with contaminated groundwater on these soils. If you're loading them in with nitrogen-rich water, you could contaminate your groundwater on these soils. So they don't filter the material as well as a soil that has more silt and clay in it. Some of the other parent material lacustrine, glacial lakes that are now drained. We do have some. All of Narragansett Bay was actually a dry lake bed at one time. We don't have any volcanic deposits here, but those would be, volcanic ash would be a parent material. We have a lot of organic soils. Some of our large swamps and bogs are all organic. A lot of our glacial deposits are overlain by a post-glacial deposit called loess or windblown material called the Aeolian. Alluvium is material deposited by gravity. Alluvium deposited in modern-day floodplains or rivers. And residuum is soils that formed in place right from the weathered bedrock. We also have a new parent material that we came up with, and actually another new soil order called human transported material. So anytime man moves or humans move materials around, and creating new soil, and that's a new parent material. So this just shows you a post-glacial deposit. We got about 70 centimeters here of nice loose windblown material, mostly silt size. That's a silt loam texture. And that's loess or windblown material that was deposited after the glacier left. At 70 inches to about 1.20 meters is your stratified sand and gravel glacial outwash. And that's an Enfield soil, which is a really good agricultural soil that we have. This just map shows you where your two basic parent materials are. How you start seeing those a lot of contour lines to the right. That's your URI, where URI is situated there. That's all glacial till. And as soon as you cross that, it says Hornbrook. The landscape levels out, and you're into one of these large outwash plains. So that's a valley where your stratified sand and gravel was being deposited there. Most of that's used for sod right now. Some of the other factor we looked at, we talked about the relief of where you are in a landscape, whether it's steep or shallow. We actually use a soil landscape model when we're mapping soils. We relate different soils to be occurring on different landscapes. So once we identify the landscape, we can start determining what we think the soils will be on that landscape. So think about where you are. If you're on a convex slope, such as where that Paxton soil is located, that's going to be a well-drained soil. The water is going to shed off of that. Water flows downhill, so it's going to be moving to your lower elevations and until you enter your drainage areas or your concave slopes. So that's what we call a soil catena, where we have all the same soils occurring on a landscape. The only difference is the depth of water as the difference there. We're going to talk about some of the properties we describe in soil, kind of the four major ones: horizon, color, texture. Horizons, color, texture, and some of the other stuff like drainage we'll talk about also. So a soil horizon is a layer of soil approximately parallel to the surface and has distinct characteristics produced by soil forming processes. We use these soil horizons to basically classify the soil and make interpretations. So you want to know the definition of your master horizons, which are capital letters. And a lot of times you'll see a lowercase letter after the master horizon. The lowercase letter tells you something a little bit more about that horizon, some of the properties there. So O is organic. You're only going to find organic horizons if you're in a very wet, poorly or very poorly drained wetland area, or in a forested area that's well drained, and the organic material is just going to be your undecomposed leaf litter. That's pretty easily identifiable. The A horizon is mineral, so it has less than 12% organic carbon, and it's characterized as having a mixture of organic material, humus, detritus, that is giving it a dark color. So carbon is in all living material, plants, animals, and that sort of thing. Carbon has a dark or is a black colored mineral. So when it mixes with the mineral soil, it turns that soil dark. That soil on the upper right, from 0 to about 30 centimeters, that's an AP horizon. That only has about 3% organic carbon in it, and it's making it that dark color. The stuff below it is the same material. It just hasn't been mixed with the organic material. So the B horizon is an illuvial, meaning something has moved in to that layer, or there's been some kind of addition, a loss, a transfer, or a transformation of that material to differentiate it from the C horizon below. So in our neck of the woods, because our soils are so young, the major part or change we see in the B horizon is just iron oxide coating the sand, silt, and clay. Iron oxide is basically rust, so it's given it a rusty appearance there to that soil. Iron is probably, aside from the carbon, iron is one of our dominant minerals that we have. So it's been referred to as the paint of the earth. So the iron oxide in a soil can either be this yellowish color that we have, or if you go to a really old soil, it'll actually be a really reddish color called hematite iron. And then the C horizon is just your unweathered geologic material. So that's going to be your glacial till or outwash in our neck of the woods. And you can see that in that horizon on the right at about 60 centimeters. The horizon on the left is actually a really wet soil. That has another horizon from about 10 to 30 centimeters. It's called an E horizon. The E stands for eluviation, meaning something has been removed from there. When I think of E, I think of the word exit. Something has exited that, and it moved into an illuvial horizon. So in, so exit and in. So at 30 inches there, you start hitting that B horizon that's got a lot of iron material and also some organic material forming that black colored layer there. And then below that, we hit R, which is hard bedrock. You know, when you hit that, the backhoe is not digging through that material there. Another thing we're going to have you identify is the color of the soil. So we use color. I mean, when you first look at these profiles, that's probably the first thing that you're looking at is the different color patterns that are within the soil, along with the layers. So it's very easily identified. We use the color of the soil to relate chemical and physical properties, such as the depth of water table, some of the chemical constituents in the soil. I mentioned iron oxide. When I see that bright color, it's telling me that that soil is well aerated. When I start seeing these blotchy colors of grays and brighter colors, that's caused by a water table. That so this soil is actually saturated at 60 centimeters for a long enough period of time to cause the soil to go anaerobic. When a soil becomes anaerobic, the microbes in the soil have reduced all of the iron, and they're starting to feed on other, they reduced all of the oxygen, and now they're starting to feed on other elements in the soil, such as iron, manganese, sulfur, and eventually carbon. And when they do that, they're reducing the iron, and reduced iron is mobile in the soil, and it's allowed to move around and get precipitated out when that water table drops. So those blotchy colors are called redoxymorphic features, and we use that to locate the seasonal high water table of the soil. So this soil, even though there's no water now, I would say this soil at some time of the year has a water table at 60 centimeters below the ground, based on the gray colors and then those blotchy patterns of grays and yellow colors in the soil. We also use soil color to identify hydric soils. If a soil is very black in the surface and then it doesn't have that nice bright B, it just goes from black to gray, that's a hydric soil, and that's typically associated with wetlands. If it has a nice brownish colored topsoil and then a nice bright colored B horizon, that would be a non-hydric soil. So to document soil color, we use something called the Munsell color system. It breaks color up into its three parts: the hue, which is the dominant spectral series. So 10YR is telling me it's a yellow red. The 10 is basically like 100% yellow red. The value is the amount of light reflected. So on a color book, it goes anywhere from black on the bottom, low chroma, all the way up to white, high chroma, like a 6 or a 8. And then chroma is the strength of the hue. So the way we document or note Munsell color, it's always the hue, the value, and the chroma. So I'll show you what a color book looks like there. Oh, we didn't talk about that. So make sure you know when we do the field thing how to use a color book. And if I say soil has a 5Y63, what is the value of that? You would say the value is the 6, the chrome is the 3, and the 5Y is the hue. I think everybody should have color books. If not, let us know. The other property we want you to look at is the texture of the soil. That's the amount of sand, silt, and clay. So that goes anywhere from very coarse sand is anything less than 2 millimeters of size is sand, silt, and clay. Sand goes anywhere from 2 millimeters down to 0.5 millimeters. That's a typo there. That should be 0.05. Silt is 0.05 to 0.002 millimeters, and a clay size particle is anything less than 2 microns. So clay is so small you can only see it with an electron microscope. It's the smallest of the particles, and as a result has some interesting features there that we'll talk about. The way we determine soil texture, basically it's determined in a lab where somebody will sieve the soil, sieve out the sand size particles. We do it percent by weight. Once the silt and clay are remaining in the sieve pans that we have, then we run what's called the pipette analysis, and we determine the amount of silt and clay within the soil. When we get back the results, we'll have something like this telling you that this soil has 10% clay. So on the left axis is percent clay from 0 to 100. So you would plot that out on that axis. 60% sand, that's on the bottom. And that goes anywhere from 0 to 100 from right to left. So we're at 60% there. And then percent silt is on the right side of the triangle. This one has 30% silt. So if you plot those out, that soil texture would be a sandy loam. Now, a little trick there for Rhode Island, most of our soils, I would say, have less than 20% clay. So you don't have to learn all of those sandy clay loams, silty clay, clay loams. And actually, most of our soils have probably less than 15% clay within them. So we're mainly looking at whether a soil is a sand or a loamy sand. And those would be pretty obvious, very gritty. On the opposite side, if it feels very creamy and smooth, it'd be a silt loam texture. And then if it's kind of hard to tell the difference, it's probably a sandy loam. So we always say if you can't tell the difference, say it's a sandy loam. That's what most of our soils tend to be here. On the field study guide, there is a flow chart for determining texture. I'm not going to go through it now, but it's basically looking at some properties. So if the soil is very sandy, it's not going to hold together very well. On the opposite side, if it does have a lot of clay or fines in it, it's going to tend to hold together well, and you'll be able to form either a ribbon or creating a wire with the soil, you know, just rubbing it like Play-Doh and then trying to get that soil to stick together there. So you want to take a look at that and calibrate your fingers. Actually, if you take soils in college, you'll spend a whole semester calibrating your hand to determine the amount of sand, silt, and clay. Almost done here. Some of the importance of texture, it's one of the major properties I would say in soils that we look at. We didn't talk about material larger than 2 millimeters. Those are treated separately. We call those coarse fragments, and they go anywhere from gravel, 2 millimeters to 4 inches. Cobble size fragments are 4 to 10 inches in diameter. Stone is 10 to 24, and anything over 24 inches is what we call a boulder. So those are described separately in the soil. So I could have like a sandy loam with 30% gravel, and I would use a modifier and call it a gravelly sandy loam texture. Some of the importance of soil texture, soil formation, the mechanics of the soil, whether or not that can support a building or anything, or roads and that sort of thing. How rapidly water moves through the soil. So sandy soils, water moves rapidly. A very clay soil, water does not move very rapidly. So you get runoff occurring in very clayey types of soils. The erodibility of the soil is determined by the texture. Soils that have a lot of very fine sand, silt, and clay, mostly very fine sand and silt, will erode a lot more. Clay actually has a net negative charge, so they tend to stick together with cations in the soil. That CEC is called cation exchange capacity. That's the capacity of the soil to exchange cations, positively charged ions in the soil, with because of the negatively charged clay particles there. So most of our soils have low clay, so we don't have a very high cation exchange capacity in our soils. Shrink swell is some clays can expand expand a lot when they moisten or wet, and that causes some issues there. Yeah, so clay has a very high specific surface area. They tend to have a net negative charge, so they can exchange cations positively charged like a magnet almost, and make those available to the plants there. So again, most of our textures in New England have very little clay, with exceptions there. Soil drainage is the depth to water table. So on this diagram, top of the hill, you can see your high water level. That's the modeled, what we used to call model, now we would call a redoxymorphic zone. And as you move down the hill, you're getting wetter and wetter. So you're going from well drained to moderately well drained, and then poorly and very poorly drained. So somewhere around that poorly drained break is where our soils become hydric. So in Rhode Island, any soil that's poorly or very poorly drained is a hydric soil or a wetland soil. The last part is just dealing with soil surveys. This is basically what I spent most of my career making, walking the landscape, digging holes, classifying the soil, developing a soil landscape relation, and delineating soils, and then collecting a lot of the background data on the soil. So we've been mapping soils for over 100 years, and we pretty much have finished most of the country except for some of our federal lands, which we're still actively mapping right now. And in some areas, we go back and actually do an update map in some areas. So you should be familiar with using a web soil survey. I don't know how I'm doing time-wise, but I can show you basically how to use that. And I recommend going in and trying to pull up a soil map for where your house is or something like that. So I'll show a couple ways to get soils data. If there's no questions.
Jim, will each school received the No Soil, No Life book? Will questions come from that book?
Yeah, make sure you read through that book. Probably especially, look into the table of contents for anything dealing with the special topic, renewable energy. See if there's anything mentioned in there. Might give you a little hint on what to look at. But yeah, definitely you want to review that. That's a really good book there. I forgot to mention that. And if a school doesn't have it, let us know. I think we might still be able to get some there. This slide just shows you basically when I was talking about those interpretations. So this is one of the beauties of our soil maps is, again, it's not just telling you the basics of the soil. It's also providing interpretive information. I can just look at this map and say anything in red is a hydric soil, 100% hydric. You're probably not going to be able to develop that. It's a wetland area, protected resource under state and federal, hopefully federal regulations. Anything in green is non-hydric, has no wetlands associated with it. And then anything in yellow is kind of borderline there. So this just shows you what we call a soil interpretation. So for the soil survey part of the test, you're probably going to be given a map and then asked to interpret some of the interpretive maps there. So this is just some slides on a special topic. Just trying to brainstorm. It's on renewable energy. So think about soil productivity. Is that soil well suited to for forest biomass production? We actually have a rating for that. Can you make a lot of renewable energies basically in the soil? So if you can grow trees rapidly and harvest them and replant them, that's a renewable energy. I got my fireplace going right now, burning wood. Geothermal, that's mainly way deep down in the soil, but there is an interpretation that we're working on for the geothermal part. I mentioned organic soils. There was a study in the 70s during the energy crisis that basically determined in the Chapman Swamp, there's enough fuel grade peat, the organic soil, to power the town of Westerly for 20 years. And we also have a lot of freshwater ponds that are really filling up, eutrophying and filling up with material. So it possibly could be dredged and used for fuel sources and improve deep water habitat. I mentioned the soil used for anchor solar structures, turbines, and etc. So basically a support thing, whether or not those soils soils can support engineering structures on them, sequestering carbon. Largest terrestrial carbon pool is in the soils. Also think about urban soils, especially in New York, where you're going, where all of New York City was basically mapped to the series level, even on their urban areas. And they do a lot of work with whether or not the soil can grow trees to keep your impervious areas cool in the summertime. So check the study guide when posted. Email me with any questions. And there is this stuff will be on that Google Drive there. So we always say, if you ever want to start a fight, put two soil scientists in a pit. So this is Donald, one of our soil mappers, about to drop a rock on Mark Stolt, the professor of podology at URI, because they were arguing whether they're on a toe slope or a foot slope landform. And I had to break them up. So shows you how we take our soils there. So any questions, or I can show quickly where to get soils data from. Oh, if I can figure out how to get this to work. Can you see this screen? Can you see this?
Yeah.
All right. So this is our soils.usda.gov is where you go to get onto the web soil survey. Again, we've changed our website, so it now requires like 3 clicks, but you scroll down here, you'll see a link for soil survey. Scroll down again, web soil survey. Scroll down again, start web soil survey. So this is how you get to the web soil survey. It does session out if you keep it loaded up here, but you would basically just type in the address. What's the place in New York where the Envirothon is?
Geneva?
What is it?
Is it Geneva?
Geneva. Geneva, New York.
New York.
See how that works. Huh? All right, so Geneva, New York. So that's how I navigate to it. This is the town. If you win, you're going to be going. And the way you pull up soils data, I'll kind of go through it quickly here, but there's I'll post the whole step-by-step or video how to do that. You first want to create the area of interest. So you draw a box where you're interested in getting soils data from. It's telling you there that there's multiple soil surveys enclosed. Doesn't matter. Now you'll see all these tabs up here start to get activated. So you can just pull up the soil map. And again, click on any of these polygons. It's going to tell you what that map unit is. The main thing we do is go to the Soil Data Explorer and start pulling up land use interpretations. So I'll do a quick one just for, let's do farmland. This is another one you want. So farmland classification is one of our dominant uses for the soils. And it's just going to show you areas that are, hopefully it's not all red, but here's the legend right here. So anything in green is prime farmland soil. So I'm looking at this area as being really good agricultural soils. We would use this basically if we wanted to put these farms into easements in our program and protect them from development. The other tab is the properties and qualities. So if I wanted to pull up tell me what the drainage class of the soil was or the parent material, let's pull that up. I'm not familiar with the parent material in this area. It's probably going to be quite complex. Yeah, see calcareous lodgement, loamy lodgement till derived from limestone. So you do get limestone in this area. So high pH soils, probably very good agricultural, high base saturation and that sort of thing. So again, this is just click through these and look for different interpretations, some physical properties, amount of sand, silt, and clay. Just a lot of information is all stored here and easily accessible. You can also do a shopping cart. You can create a customized soil survey report. And that's what you're going to have to look at during the field. We're out doing the exam day is a report that I will generate and print out for you. The other easy place to get soils data is something called the Soil Web. Let me see if I got that on here. So you just Google Soil Web. Where's my tabs? On here, let me just do. So Soil Web is also uses our national data, but it loads a lot quicker and you can just start zooming into an area, and pulling up soils data by clicking on it and getting a lot of information here. It's also available on a cell phone. So if you have a smartphone that you want to pull up your soils data, download the Soil Web app and start hitting it and learning about your soils. So I can click on this and get a lot of information about the soil very easily without having to identify areas of interest. It'll also go right to your location with the little GPS thing. I can change the base map to be imagery. And you can also get a whole bunch of data if you do the Soil Data Explorer. You'll be shocked with the amount of data that you can get, lab data, all kind of stuff. So real good source for data is the Soil Web. And I think that's it. My hour is up. Any questions? If you do have some, you got my email address. I'm usually available.
Thank you for that.
Yep. Let me stop sharing. See if I can get out. Sorry about all the issues with my sharing. You figure I've been doing this long enough, and I should know this.
If you kids have no questions, feel free to go.
Okay, we're all good.
Right.
Yep.
Jim, I put the 2016 Rhode Island Soil Manual that you sent me.
Oh, okay.
In the Rhode Island Envirothon files folder for all the teachers.
Okay. Yeah, that's one that I thought I had sent for the website a while ago, but that's yeah.
It went out to all the teachers in 2016.
Okay, back then. Yeah. So that's just one that has a lot of stuff in a PDF there. So it's a pretty good one there. And if they do need any books or color books or anything like that, they should get in touch. And we can get some of those there.
I don't know if Natalie has any of that stuff.
I don't know if she has that or
I
Beth
don't.
has that either, but they probably don't have the soil book that he showed and the no soil books.
No, I don't have any of that, but anything would be much appreciated. This
Color
was
books, you mean?
awesome.
Or,
Thank you, Jim, as well.
yeah. You mean color books too? Or
Yeah, we just started, so
okay.
we're starting fresh.
Okay,
All right. Good.
we all set?
I might-
I'm gonna stop the recording.
I might still have some the books that Mark Stoltz gave us. I might only have like 1 or 2 copies left.
Yeah, he uses the Earth Color book, or yeah.
No, he gave us via one of those contracts or gifts that he gave us like 10 copies of the no soil book.
Oh, okay. Oh, no soil. All right. Yeah.
And Jim, I think you got one of those as well.
Yeah. Yep. Jillian gave me
Yeah.
the copy. Yep. Yeah. If you need more, again, our society has, make sure every year you request funds from the Society of Soil Scientists.
Yeah, I did send them a letter.
money. Yep.
Yeah, I sent out about 30 or 40 letters in the last
Okay. Yeah.
week or so.
It should have been approved. So if you haven't heard back, let me know.
Oh, no, you guys are very good to us.
Good.
Very generous.
All right.
All right,
Okay.
thanks, Jim.
Yep. See ya.
Thank you very much.
Yep.
Thank you,
Bye.
Jim.
Yep. See ya.
Bye.
Bye.